I am very pleased to be here to present and to have our speaker to present a talk on hardware security mechanism for authentication and trust. And the speaker for today is Professor Farinaz Koushanfar. She's an assistant professor of electrical and computer engineering and computer science at Rice in Texas, where she also directs the TI-DSP Leadership University program. Before joining Rice in 2006, she received her PhD in electrical engineering and computer science and her master in statistics, both from UC Berkeley. Her research is focused on developing techniques for synthesis and management of customizable, adaptive, lightweight, and secure embedded systems, adaptive energy delivery, and application of emerging technology. Farinaz is a recipient of an ONI Young Investigator Program Award, an NSF Career, a DARPA Young Faculty Award, and an Intel Fellowship, and also a Mobicom Best Paper. In 2008, she was named one of the MIT Technology Review Young Innovators under 35. So please welcome our speaker, Farinaz.
Thank you. Thank you very much, Mani. Advances in technology and applications, together with emergence of new business models, create a need for new security mechanisms and technologies. A particularly effective class of mechanisms are those that are being implemented in hardware. What I will talk today is about couple of these mechanisms that we have been working on, and those that are proving to be effective in a number of security and protection cases. Let's take a look what has been happening in semiconductor industry the past 25 years from a completely vertical business model where the design and manufacturing has been done in one company. We have gone through a completely fabless business model for a large segment of an industry. Here I'm showing that 25% today of the whole industry is on the fabless business model where a company is designing its chips and then sending it for fabrication to another fab to be fabricated. Of course, this 25% may be misleading because if you look into the leading edge technology, the percentage of fabless companies is a lot more. Now, what happens is that the fabless company is paying for the mask, which is really expensive. The cost of building a full-scale mask is really a lot, and then the company who has the mask can, once the designer pays for this, can build many copies of the chip. And this is partially helping the problem of hardware piracy. There is an astronomical report of how much hardware is being pirated every day, and a large percentage of this has to do with the fact that the designers have to expose their IP to the fab, and this is the whole effort and the whole belonging of this company that have been working on a product for for years. And what exacerbates the problem is that hardware vulnerabilities facilitate program and data piracy. So this problem is a problem of crucial importance. Now, hardware metering is a potential method how to solve the hardware piracy problem. This is a problem that has been captivating me for over a decade. Basically, how can we ensure that once the designers design an IP and send it for manufacturing, have post-manufacturing control over the IPs that they have designed? And the original methods how to do this have been passive, basically monitoring the number of manufactured ICs ICs from one design. And then this helps a lot in litigation cases if you catch designs that you suspect are coming from what you have designed, but this actually does not help preventing the problem. And the big question has been, how can we have an active method for doing this? Can there be a possibility of the designers having control of each copy of the designs they have in a chip, controlling the activation? Can they monitor what is going on with their IPs while they're in use, enabling and disabling during the runtime? And this is going to be the subject of the talk today. I'm going to talk about the steps that we've taken in developing the first known active metering method, how this problem can be solved. So for us to have an active way to meter hardware, the first question is, we have to identify and authenticate each piece of IC uniquely. And for this reason, we're going to talk about unique unclonable identification based on the unique fingerprints of process variations of each IC. I'm going to talk about ongoing efforts in security analysis of these structures and all the way to implementation, new concepts, and fabrications of these devices. After that comes the key part of hardware metering, and that is, once we design an IP, can we have access points to the functionality? So somebody who does not know how to access this functionality would not be able to operate it even though they have the IC in front of them. And for this, I'm going to talk about our method for alterations of the design structure to include unique access points to the IC's functionality. I'm going to go from foundation all the way to mechanisms and hardware synthesis and implementations on real hardware. And then the question is where all this is going. So just to be self-contained, I'm going to give a very brief overview of what are physical unclonable functions. These are hardware mechanisms that have been introduced for identification and authentication of chips. If you look into what happens in a traditional authentication scenario, and verifier sends a challenge to the prover, and if the prover has a traditional security protocol running, it has a key stored somewhere, it's going to send a response signed by the secret key that is inside, and that's how the verifier verifies the authenticity of this device. The limitations of this mechanism is that the key is stored somewhere in the physical device. So if you're running, something that has to do with hardware, you have access to those. So your notion of secrecy can be corrupted, or if you have a very small device, it has been shown that such keys could be broken using side-channel physical attacks. And the other thing is, of course, if you're running on a small-scale embedded systems, running these protocols are very resource-intensive. And physical unclonable functions are taking on not storing the keys, but using the mesoscopic fluctuations of a physical phenomena as a secret how you would authenticate a device. And this is possible in silicon, as it was shown that because of the process variations in modern technologies, no two ICs, even coming from the same mask and the same design, have exactly the same characteristics. And this has been used in introduction of the first set of the delay-based silicon physical unclonable function by Professor Devadas and his group at MIT, where the authenticator sends a challenge to this device, and then based on the unique timing of this device for the responses, can authenticate this device. And here is a physical implementation of this device in hardware. What happens is that a signal comes in this path, and then a device is authenticating at the end of the path which of these two paths that are identical by construction, but because of variability are different, which of the signals is coming faster. And then there are selectors that select the two paths. For example, let's take a look what happens. Here, the two paths are identical, but the signal arrives earlier. The blue signal arrives earlier, so we get a 0 here. If we change the selector bits, we get another path, and now here, the signal above comes earlier. And then you can get an exponential number of challenge responses from the same device to authenticate it. Now, when we started looking into PUFS, because they're very attractive in many senses. We are not storing the digital keys. If you want to be at the hardware level where somebody has access to hardware, that's pretty much the only option we have to use. But the first question to ask is that, are these structures secure? And that's what we started analyzing. So first, the first thing we did, we came up with a set of desideratas for hardware security based on properties including randomness, uniqueness, and the reverse engineering of the challenge responses. And the first arbiter-based PUFs that I've just described are actually subject to linear attacks, because even though you have exponential number of combinations, you have a linear number of ways you can add up these delays, so this can be broken. And this was actually pointed out early on by the MIT group, who have introduced a number of methods how they could overcome this problem. And their main trick was to use nonlinearity in the system. Here I'm showing one way how nonlinearity could be introduced. And here, in the middle of the signal path, another arbiter which selects between the speed of the signal is fitting forward to the front. And then that introduces one nonlinearity in the system. So if you can imagine adding many such nonlinearity, you can protect your system against potential reverse engineering attacks. And the first thing we've shown was that this could actually, based on the partial linearity in the system, we could run a machine learning attack that could break this system. So the short answer was these are not secure. And a year after us, a group of German researchers have introduced another algorithm which was slightly faster than what we had, and again shown that this system was breakable. And now the question was, how can we safeguard these? If you introduce, so one possible solution was to introduce hashing, but hashing was again not secure because our way to break the system was not based on controlling the challenges, but of course you would know the output of hashing could break the system. So our way to address this problem has been to block controllability and observability into these devices. And to do that, we have introduced different types of blocks, basically transforming the challenges, controlling controllability, and we did that with an interconnect network and blocking observability. I'm going to go very quickly through them. So transforming the challenges, the basic idea was, if you want to have a system that is not learnable, every time we change a challenge, the probability of response changing has to be 0.5, which is also known as a strict avalanche criterion. And what we did is we did probabilistic analysis and find the challenge transformation which constrains the interrelationship between the selector bits that could achieve this. And let me just give you a hint how this worked. Basically, what we went on was, if you look into that equations of the response, which is the sign of the sum of the delays that are to the power of this transformation, if you analyze this probabilistically, just assuming that you are having each of these delay differences has a mean around 0, then you would realize that if you have a challenge transformation which flips 2 bits that are almost half the path away, you would get the perfect probability for the strict avalanche criterion. So we introduced a transformation that did that. And then after that, we introduced a permutation way to interconnect the challenges and takes the control out of the individual challenge bits. And then the perhaps the most important part for reverse engineering attack was blocking observability, and that we did by taking the space of the challenges, the responses, and transforming it to a smaller space, such that the probability of going to the smaller space to the larger space, every time we got exactly 50%. And we did that with a simple XOR network. Here I'm showing an example. So basically here, two different sets of responses map to one. And if you have one response, you don't know which one to go back. And if you analyze the complexity of this system, if you map Q response bits to Q prime response bits, even though the size of this output circuit only grows linearly with n, the reverse engineering complexity goes as exponentially with n. And let me just briefly show you some results. Here I'm showing the output transition probability after adding the input network. So we see that after adding the transformation, we got exactly 50%. The transition probability went, which is the variance around the 50% point, goes very low as long as we have a long enough PUF and we have a good enough compression. And also, the interconnect network constrains the amount of controllability, so we were very secure against the fault injection attack. Here I'm showing a fault injected at one of the switches, and the same fault injected in the lower circuit, but nothing changes for the case where we have the interconnect network. And just to give you an update, there were two groups of researchers that have been working for the past 2 years trying to break some of these methods. And so far, they have not been able to break especially the compression network that we have described. Okay. So far, I talked about one set of mechanisms that could be used. Yes?
So I just want to understand something for these PUFs. How would they be used if the chip is fabricated and you don't know what these delays are? How is that? But you can get the signature out. How is that useful, sort of in the context for somebody who didn't have the information? I mean, do you have to learn the information from the chip?
Yes.
Before it's useful, or?
Yeah. Well, for the PUFs to be used as a challenge response, you have to have a database of challenge responses. And this database in the original PUF proposal should have been exponential if you wanted to have exponential number of possibilities. One thing I will not talk about is our methods how to make this database polynomial size. But this is correct observation. You needed to store all the challenge responses. PUFs were one example how manufacturing variations could be extracted. There are other ways to extract manufacturing variation, and this is another way that we have been working with IBM research on new circuit design structures that can have the PUF mechanism. And instead of using the delays, now we are using the currents. And there are a number of advantages of using the currents. So it has a much lower overhead in hardware and area. It has larger variations. It has a higher degree of freedom in laying out. We are not constrained by the pad structures. And we have a much larger challenge response space. So this is a project we are scheduled to fabricate at the IBM Trusted Foundry under the DARPA Trusted Access program, and the project is supported by SRC. So a lot of people in industry have been interested in this application, in particular because they're looking for ways how to do RFID in a small form factor. So we were notified this January that the TI security group has added itself through SRC as an industrial liaison to this project. And this is going to be fabricated 9LP CMOS. Okay, so now that I've talked about how you could extract unique process variation-based IDs from your chip, the question comes, how can we make this unique access control to each IC's functionality? And since the picture words 1,000 words, let me just show you what I mean by this. So a PUF is somewhere there generating an ID, and somewhere there I have the chip's functionality. How can I make this functionality to be a function of these unique variations of the chip, such that for somebody who does not know these functional specifications, this works as a unique lock to my IC. So I need a password, in effect, to get into the IC. So this is the higher level flow of active hardware metering. I'm the designer. I take the design description. I go to the finite automaton domain. Then I go through the steps of the design, most time consuming, probably time enclosure. Then synthesis, mapping, placement, and routing. I have the IP. I take this IP. I send it to the foundry. I pay for the mask. The foundry makes the mask. And now, once the chips are coming out of this mask, they're going to be locked. They're not going to be functional. And the only thing the fab is going to send to me is a set of scans from the flip-flops of this device. And then after this, I'm going to calculate a unique key for each chip and send it back to the chip to unlock and activate the chip. And this is just the basic flow. Of course, these mechanisms will give you a lot more in terms of controlling your devices once they're deployed. Now the question is, how can I implement these locks? This looks like a not very easy problem because the mask is unique and it's very, very expensive. So you cannot alter the mask uniquely. The assumption and models, we are talking about an adversarial model where somebody has a full access to our whole design, from our netlist to OSIS files to the test vector, and they know every detail from whatever we've designed. On the other hand, any substantial design alteration would require time enclosure and going to the steps of the design, which is almost as hard as designing something from scratch. So these are not economically viable attacks. And going through these phases is as hard as designing a new ICs. And then there are different attacks, and they have different costs. So there are attacks on the netlist level, which you have to still go through the time enclosure and all those steps in order to get the IC. There are attacks on the OSIS level, which are very constrained and very expensive because you really cannot have a large degree of freedom in your layout once you have it. And then, of course, there are attacks on the mask, which are extremely, extremely constrained. So after you have a mask, the most thing you would be able to do would be at most to cut some wire or to add some wire in a certain number of cases. And that's pretty much the only thing you can do. So what do we really mean by this unique functional access? Let's go back and take a look into sequential circuit specification. We have a sequential circuit specification that the designer has in the finite state machine format, and then the designer goes through the design process and gets a compilation of this program in terms of a netlist. Now this compilation has exactly the same input-output characteristics as the original finite state machine. And this netlist is completely publicly known, and the access, we want to activate the access by a sequence of input and passwords. And now, if you really think about this problem, this is indeed an obfuscation, right? We have a compilation of the program where we have exactly the same input-output performance, but what is inside of the second program is completely known, and we want to hide stuff about the first one. And then when you think about obfuscation, perhaps the first thing that comes into mind is that there is a very famous work around 10 years ago which says obfuscation is impossible. So how do we go about solving this problem? OK. So let's go back to in what setting has been shown that obfuscation is impossible. The original result of obfuscation, impossibility of obfuscation, was saying that if you have a generic program and this generic program you want to obfuscate it, you would not be able to obfuscate, and the way to show it, they showed it, is that they have introduced a family of functions that could not be obfuscated. So this was not done for the general family of functions, and this was actually proven for two classes of oracle models. One was the exact oracle model, where the two compilations have exactly the same functionality, only a polynomial slowed down from one to the other, and this is a virtual black box. Then the general obfuscation in the random oracle model has exactly the same properties, only the difference is that the two compilations have to have slightly different functionalities. And these two were shown to be generally not doable for any program. But however, there was a positive result that came out a few years later, and that was the provably secure obfuscation of a point function under the random oracle model is possible. Now let's take a look what are point functions. So a point function in a very high-level view is exactly a password. You have a system, and you can enter a password to the system and get into the operation to get the system to work. And we use passwords every day, all the time, basically. And we assume that they are secure as long as we select a secure enough password that cannot be guessed. So here, you know, if there is a system that is basically having this point function, it has been shown that this is efficiently obfuscatable under the random oracle model. Basically, the probability of somebody finding this password is extremely, extremely low. Now, this result has been generalized to point functions with general outputs. So if instead of one bit of output, you have a number of families of output, then you would be able to obfuscate this system under the random oracle model. And also to multi-point functions with general output. So if you have a system which has not just one password, but a number of passwords to access the system, you still could efficiently obfuscate this program. So let's go take a look back into what we had at the functional level. We have a functional description of our circuit, which is in form of finite state machine. And here I'm just putting a formal definition of a finite state machine. And this functionality can be shown by a graph, also known as a state transition graph. We have a set of states. We have transitions between the states, start state, accepting states, and an output function that defines this finite state automaton. Now, our problem was, how can you build a STG-based, graph-based access control system? So given an original directed graph, our objective is to add a number of states and transitions to obtain an obfuscated directed STG, which has additional Q prime additional states and E prime additional edges. And for us to do this, we need to define an access function, which takes us from these obfuscation functions, obfuscated states, to the original states that we are putting as a secret. And this access function is going to be only activated if we input the transitions, the inputs that make us transit from an obfuscated state to the original state. Now, if you want to have a chip that a design which can be activated uniquely on each of the chips, what you really want to have is not just one point function, because on each of the chips I'm going to use the same design to have multiple of these access points. So I'm going to have to use exponentially many access control points to get into the system. And what we have shown is that this is again a multi-point function with at most Q prime D points where the output is not valid, and because the probability of getting to these places using the passwords is really, really low, the system under the random oracle model is still efficiently obfuscated. another thing that can be shown under this multi-point function is that if you reveal parts of your graph to somebody and you give them the password, still, if you design your password system well enough, you're not somebody who has this partial information would not be able to come up and find the other access points to the system. So let's see how this works for our system. Here, I have an original design in a toy example of 8 states that can be stored in 3 flip-flops. I'm going to add 3 more flip-flops, so a total of 6 flip-flops for both the added states and the original states. So I add 54 additional states. Now assume that I have a chip with a unique identifier like from a PUF, and because of this, my chip would start in a random state. Now for somebody to go from this random state to the original states where the chip was functional, they need the right password that would transition them from this state to the original states. Now, of course, one of the big questions is how do I create passwords that makes this secure? And this is a problem that can be easily addressed. I just create the password, sign it by private key of a public key system if I'm the designer and I want to prove later that I'm the person who designed this access point system. And then after I get a fixed bit message, I basically use this to create a sequence of inputs, and I modify my state transition graph to include the added edges by adding also to the states. Basically now I have both the states stored in the six flip-flops that I had, so there is no way for anybody looking into the system to basically distinguish between the 2 sets of systems that have been available in my design. Now, to ensure a proper operation, I need to make sure a few things. One is that the probability of powering up in one of the added states is sufficiently large, and this seems to be reasonable, doable with a reasonable overhead, just because by linearly adding to the states, I'm exponentially adding to my state space. And then, of course, the probability of collision has to be satisfied by considering the birthday paradox problem. What is the probability of getting random chips that are storing in the starting in the same state? The low overhead of the added states, diversity of the keys, and the storing of the input sequence, which would activate each of these chips uniquely. And so there are a number of attacks that are possible on the system, and I'm going to address these attacks. The first set of attacks have to do with guessing the passwords by brute force attack with memorization of the previous passwords, and reverse engineering of finite state machine. The second class are the ones that have to do with reverse engineering the PUF, trying to capture and replay the initial power-up state, the reset state, and the control signals. And the last class of attacks are basically creating a large number of ICs, hoping that we will get to a point where we have identical instances and combinational redundancy removal on the chips. In developing countermeasures to the attacks that I've just described, there are 2 things that are in our favor. The first is that in modern integrated circuit, finite state machine is way small part of the whole design. So even if you add a lot to this finite state machine controller, you're not going to add a lot to the overall design. And the other one is that the multi-point access control can be efficiently obfuscated. Now, for somebody to use the brute force attack with memorization and reverse engineering of finite state machine, the countermeasure is simply selection of strong enough passwords and provably efficient obfuscation of access points to the finite state machine. Of course, the removal of the PUF initial power-up state capturing and replaying, and initial reset state capturing and replaying, and control signal capturing and replaying can be avoided by making these transitions and state insight by basically two types of countermeasures. One is to interleave the physical unclonable identifiers within the circuit so they cannot be removed, and we have a number of PUF designs that satisfy this constraint, to actively check the existence of the PUF in the circuit, and also to make the edge transition a function of the unique unclonable variation. So what happens is that if I have a password to one of my chips, and I'm going to replay that on the other chip by replaying the initial state and the password, I can make sure that these transitions are also a function of the unique variation, so they cannot be broken. Now, there is also this attack of creation of identical ICs by just making a huge number of them, and this is not economically very viable. The combinational redundancy removal is also not very possible, because this is only a method that works at the verification level and for very, very small circuits. And now this all can be avoided by decreasing the collision probability by the design. And what has been actually really interesting is not just creation of mechanisms that can create a method to have access point at the foundry level, but now we have a way to get access points to the chip's functionality by only the original designer. And this could be used not just in the original setting that I just described, but it could be used for enabling remote control, disabling, and for third-party IP protection. So a number of, since the introduction of the original hardware metering methods, a number of methods based on the mechanisms that was introduced has been used for protection of intellectual property in settings where the designer does not have a control over who is using their design. Here I'm showing one example in terms of in case of a tamper detection. What you want to do, you really want to go to a set of black hole states where your functionality is not well defined. And now, unless you know the right way how to come out of these black hole states, you would not be able to address this problem. Now, of course, this was all good and beautiful at the theoretical level, but the question was, how can we efficiently build this in hardware? The problem is that the synthesizers that we have to synthesize a design from a description level to the hardware level are not exactly optimized to allow these access points. And in order for us to generate these circuits, we had to go around the synthesizers. Basically, what happens if that you include all this huge state space that we've created with the original states and give it to the synthesizer, it's going to make a huge circuit. And even though the controller was a small part, still this would add a lot of overhead. For us to address this problem, we went on by adding a wrapper to synthesis, to the ABC synthesis tool, basically doing not just synthesis once, but iterative resynthesis. And after we did steps of the iterative synthesis, we basically did a timing closure on the circuit. Basically, what you can do is you can first imagine separately synthesizing these circuits and then iteratively interleaving them together to get a very low efficient overhead for your implementation. Now, I'm going to talk about the first set of experimental results on the benchmark circuits. Here I'm showing a set of combinational circuits from the ISCAS benchmark set using the ABC synthesis tool. And there is, this is the percentage increase in the area. And as you can see, there is, for very small circuits, there will be an amazing increase in the area. But if you think about that this component is way less than 1% of your total area, you're not adding a lot to the area. But even then, as we increase the circuit size, so we go to a little bit larger circuits, which are still very small, with like 18 input, 19 output, we get around only twice the overhead. And if we go to anything a little larger, we get the overhead extremely low in terms of the area. Taking a look into how much are we adding to the power and delay here, basically for the different circuits that we have. Again, if we are looking, first of all, the timing is not going to be affected, because once the circuit is functional, its functionality is going to be the same. But the power will be affected on the smaller design. But if we take a look into the same two designs, for example, here for a very small, still very small circuit, we get about twice the size, the power for this small component. And if we add a little bit to this design, we get in the order of 13% to this small part, which is very, very negligible to the whole design. But but if we look into slightly larger design, for example, we did do proof of concept implementation on FPGA on H.264 MPEG codec player. What happens is that if you synthesize this design on an FPGA, this is how many LUTs and gates you get. Now, if we add access points such that we get 2 to the power 20 possibilities to enter the system with different key lengths, as you can see, we get very, very low overhead in terms of the percentage of the gates added and the percentage of LUTs. And to me, as a designer, the H.264 is still not a huge benchmark, because this benchmark is typically used in conjunction with a number of other benchmarks. So the overhead can be effectively extremely low on this circuit. So now that I've described this two basic mechanisms, the first set of mechanism was based on the fact that you can have identification based on the unique mesoscopic variation of your physical phenomena, and then the fact that you could basically alter the design structure to include multiple access point entries to your system. We are going to see where this can be all going. So the mechanisms and protocols that have been so far introduced for PUFs that have been basically introducing a symmetric key mechanism. Basically, there is this key stored somewhere, and this key that we have stored somewhere, if somebody has the database, then they would be able to verify this because they know the secret already. Now, a big question is, we all know the advantages of one-way cryptography. The big question is, can we use these hardware mechanisms to build a one-way physical unclonable function using these structure? And this is still an open question. There has been a number of initial progress reports on this. Basically, if you think about the simplest mechanism that you can take is that if you have an original device and you look into how this device can respond to challenges, what happens is that this device can respond to challenges much, much faster than any simulation or emulation of the original device. Now, if you put a time bound on the system, basically say, how fast can somebody make this response happen? If you have the original device, you would be able to authenticate with a time bound. The only person or entity that can authenticate this is the original device, and no other entity would be able to authenticate that. But of course, this alone can only introduce a notion of transient security, because if you have all the time to compute, you would be able to beat this security system. Now, if you want to have more than just transient security, what you can think about is having circuits that have inside them certain computations that cannot be replicated by others. And there was actually a nice proposal by a couple of my colleagues that has appeared last year in building those, but we have, which was working based on the timing of the glitches inside the circuit. So they have shown that this system is indeed possible, but there are two problems with this proposal. First of all, the glitches are not going to be always viable. So if you have a working circuit, what happens is that a lot of glitches will be absorbed in the middle. The other problem is, of course, the fact that they rely on a very precise timing in the order of 10 to the power minus 15, which is not always possible to do by external clocking to get the internal clocks. So this has not been practical, and this is one of the problems that we work currently at MIT with Professor Devada's group, trying to find new circuit mechanisms and constructs that can address this problem. Another place where PUFs are extremely useful are on FPGAs. On FPGAs, because of the limitations of the technology, we cannot have non-volatile memory. Now, now for us to do authentication, we need other means to authenticate FPGAs, and especially IP protection on FPGA has been a big issue. So the mechanisms that I introduced for introducing access points to the IP running can be used for this type of authentication. There is a growing effort in developing new hardware structures and mechanisms. Basically, how can we uniquely identify each piece of computing component, and not just by looking into the current silicon technology, but looking into emerging nano and biotechnology and see how these variations behave. The lightweight mechanisms that are provided by the PUF can be used to build lightweight mechanisms for protecting software and content, and there is more and more move towards this type of security. And hardware IP protection issues are different for hard, soft, and firm IP models, and these are all going to be of increasing importance. Another problem that is being actively addressed by our group is hardware Trojan detection. Basically, how can you detect if somebody has added additional components to your design, even during a synthesis or after fabrication? How can you detect that, and how can you use the information that you embed to prevent these type of attacks? And our method to address this problem is to go through characterizing the circuit. Basically, if we have a design, we need to be able to characterize it, to be able to say what has been added. And our method for doing non-invasive characterization is a combination of statistical processing methods and with profiling. And using this, we have shown earlier, for example, if you perform compressive sensing in using the post-silicon data, you would have much more efficient characterization, which could also be used for Trojan detection. For FPGA characterization, we have shown that if you use methods from signal processing, we could get up to 3 orders of magnitude. In conjunction with clock synthesis, we could get 3 orders of magnitude improvement in characterization compared to the state-of-the-art methods. And in general, it is my belief that as we move towards nano and biotechnologies, and as we have structures that have increasing amount of variation, and as these geometric shapes are going to be of increasing importance, we are going to need more image processing, statistical signal processing methods to address those problems. And a number of projects that we are pursuing here is how you could integrate these efficiently with sensing of the components. So what I have talked about today has been a finite state automaton here, where we had a number of original states, and then we added to this state space to get flexibility to this system. And this flexibility helped us to adjust to the unique variation of the system for the purpose of security. This is only one example of the general line of research that we've been pursuing in n-variant design. What are n-variant design is that instead of, if you think about application-specific design, people have been going for years to make it more efficient and low overhead. Otherwise, you would make the programmable solution. And for doing this, you lose flexibility. And in order to gain this flexibility back, there are a number of higher level variant embedding that can be used. And then what happens is that if instead of only one option, you have n different variants of your option, and if you have variation in what you need from your system, you can adapt to these to get a much more powerful system. For example, examples of things that can be variable in your design are the fluctuating fabrics. So as we move towards the smaller technologies, we get more variation, fluctuating workload, and as we move towards new energy sources, fluctuating energy sources. So what happens here, for example, how n-variant can help is it can help by adjusting your system to these variable energy sources, so you would have a much, much more energy efficient system. So in conclusion, what is really emerging is a number of new threats because of the emergence of new business models, a number of threats that are threatening our microelectronic industry and the systems that are built upon them. For addressing these problems, we need new mechanisms and technologies, and in order to develop them, we have to look hard inside the hardware and the ways that we design our hardware and systems. Today, I introduced two such mechanisms: how you would be able to extract unique fingerprints from your chips, how you would be able to do functional level modifications for creating secure access. Now, where I'm hoping to go is using characterization to learn the properties of the system, either the fluctuations at the manufacturing level, or the workload, or the variable power sources that are available, and build these adaptive customizable systems that can adapt as we run to these unique fluctuating resources. And all this would not have been possible without the effort from my group, my postdoc, Golsa, my graduate students in computer science, Yusra and Nathaniel, my electrical computer engineering graduate students, Mehrdad Ahmed and Azalia, and my undergraduate students. And my research during the past 3.5 years have been generously supported by a number of funding agencies and companies. And with that, I would like to conclude the talk and open the floor for questions. Thank you for your attention.
Okay, yeah, go ahead.
So I think the notion of a PUF is very interesting. I'm particularly interested to find out where PUFs are the most useful or being used today. I guess I might frame my question in two ways. One is, where are PUFs used today, and why are PUFs the right solution over something like tamper-resistant hardware for those applications? And then also be interested in hearing where do you think tamper-resistant hardware is actually the right solution over PUFs for PUFs?
PUFs are, as I mentioned, they're getting more and more attention from industry. One area where I believe Professor Devados is taking this is he has a startup which will have a product this summer on the market. So in some sense, we have to wait to see what happens. But as I mentioned, both the TI primarily RFID group and IBM research group, which does because security and privacy are extremely interested in PUFs. And the reason you're interested are two. One is the fact that this is a much, much lower rate than a traditional crypto. So this saves us a lot if we have embedded systems that are low power with a low power footprint, but also it has this property that the keys cannot be learned. Basically, if you have a public key or a tamper-resistant system which is built on a crypto, then the assumption, it would be subject to a number of attacks. And the existence of these fluctuations that are really deep down in the hardware and can be queried really deep down in the hardware can help you a lot in building systems that are very, very low overhead.
So you had the quote of $1 billion a year, $1 billion a day in people stealing hardware. What's the general mechanism of how this is being stolen? Who's doing it now?
So that's a great question. If you look into this, of course, this is only partially because of the exposure at the fab that I just described. But the observation is in a number of gray markets, you see all these devices that are doing all these functionalities that are really, really complicated. And there are only a limited number of fabrication facilities. I showed the number for updating a fabrication facility that are able to build this technology. And now the question is, how did somebody build it? If somebody has built it, one of these companies has to have pirated it. So there are, for example, I can just quote you some numbers. A few years back, I think 3-4 years ago, there was reports of $500 million piracy in cell phones in Korea, pirated cell phones in Korea. So the bottom line is not everybody has this technology. Actually, most of the leading edge technology is still in US in fabless design companies. For example, in the fabless design model that I showed in my first slide, 9 out of the biggest 10 producers of these IPs are US companies. So there's still a lot of technology that is being built that is leading edge and is being leaked somewhere. Yes?
So the PUF does not have the key stored somewhere, the short description. There's no short description of what the PUF does, right? So how, if I understand correctly, so if I've got these devices, how do I control it anymore? What as a designer who's received these chips back and so on, how do I control the PUFs, the action of this chip any more than an adversary? What extra information do I have? Is it just extra time to extract all these combinations, or what is it that I have that the adversary doesn't?
So what you have that the adversary doesn't depends on the attack model, right? So in the attack model that I described, I was just trying to show protection against the foundry attack. Now, if you want to protect against the other ones, for example, who's using your IP, there should be a notion of a trusted third party, as it is the general notion in such scenarios, that has tested and has the data for your PUFs to basically for you to be able to control this IP. And you said correctly, basically, if you want to know the responses of this PUF, you have to be able to measure it at some point. And as I mentioned, we have methods how you could make this compact. Basically, at the end of the day, no matter what you think, there is a limited amount of the delay combinations that are inside the circuit. So our non-invasive characterization, we have a number of methods how you could efficiently do this, but of course you have to make sure that somebody who may be the adversary would not have controllability and observability to your characterization mechanisms.
Okay, well,